Hello, I am Steve Shulka, Chair of the Statistics Division. I'd like to welcome you to this month's webinar offering by the Statistics Division at a little bit later time than we typically do. The Stat Division would especially like to welcome members of Section 1213 and a few other sections from Region 12 to this webinar in the spirit of cooperation between member units. For those that stay throughout the presentation, you will earn 0.1 RUs for those that need recertification. An email attesting to your attendance should arrive tomorrow to your email. Microphones have been automatically muted. If you have a question, use the chat feature to send it, and either Adam or myself will respond. For a listing of future webinars that are available free of charge, go to asq.org and look at the calendar of events. Tonight, our presenter is Adam Pintar. Adam works as a mathematical statistician at the National Institute of Standards and Technology, or NIST, outside of Washington, D.C. He's been there for the last almost 8 years. He has a PhD in statistics from the Iowa State University. He's a member of the American Statistical Association and is the past chair of the Statistics Division. At the end of Adam's presentation, after we do some questions, you'll be sent a survey that hopefully you'll respond so we can improve on future presentations. And this webinar will be found eventually, maybe within the following week, on our YouTube channel, which you should be able to see on the display panel. With that, I will turn it over to Adam and an introduction to ANOVA.
Thank you very much, Steve, for the introduction. So usually I'm on Steve's side of the microphone. I usually moderate these webinars. I appreciate Steve asking me to do this one. And so there was one thing I wanted to mention. So I found when I was practicing this weekend, I was pointing at the screen to highlight things, and I had a realization that wouldn't quite work in a webinar. I'm a little more used to giving presentations in person. So if I'm speaking and it sounds like I'm actually pointing at my screen and you don't understand what I'm saying because I'm saying, look at something, please ask a question. And Steve said to use the chat dialogue, but actually there's a separate dialogue called a questions dialogue for you to use. So there's a chat dialogue and a questions dialogue. If you try to use the questions dialogue, I would be most appreciative. Let's see. I will do, sometimes with webinars, we do questions at the end. If you have a question while I'm going through my presentation, please feel free to ask it, and I will keep an eye on the questions dialogue and try to stop and address questions as we go through. And then hopefully at the end, or we may have some more questions at the end, we'll have another question and answer session at the end. As Steve said, my presentation will be about analysis of variance, or ANOVA, be a fairly brief introduction to it, getting to know about ANOVA tables, some interpretations of the components of ANOVA tables, an example. There'll be an example that I go through that's relevant to my own work, but I think that you'll find easily relatable, that I will use for context as well as for motivation. Okay, first question, will the presentation slides be available? The presentation slides, yeah, we'll probably make them available eventually via the Stat Division website. Our first priority, though, will be to make the video available via the YouTube channel. So that will probably be available as quickly as I can get it approved for release through my work. All right, so let's begin. Some preliminaries. First, ANOVA, as I've already mentioned, stands for Analysis of Variance. And the goal, and something I'll return to several times, is that what we're doing is we're partitioning the total variability in an observed set of data. And the reason we do this partitioning is to attribute the parts of the variability to specific factors. That sounds pretty abstract at this point, I realize, but I will return to that. I wanted to get it out there right away, and I'll return to that several times throughout the presentation. The other thing I wanted to mention as a preliminary was that I will attack this from the point of view of predictive modeling. So we'll try to interpret the components of the ANOVA tables in that way. That may be different if some of you have done courses or short courses that included ANOVA before. That may be a slightly different way to think about analysis of variance, but it is my preferred way to think about it, and it's a general point of view. So it doesn't just work for one factor ANOVA and two factor ANOVA tables. It works for as broad as you want to expand them. So as many factors as you have. The example scenario that I mentioned, and this, as I said, comes from my work at NIST, are standard reference materials. NIST produces standard reference materials and sells them. Typically, they are artifacts, and they come with a certificate that states a value of a property of the artifact. So one group of artifacts I've recently been working on, as I've pictured on this slide, are bottles of coal. So this is ground up coal. So NIST buys coal, or obtains a lot of coal, grinds it up, mixes it to homogenize it, and then bottles it, and certifies, as the labels on these bottles say, sulfur and mercury in that bottle of coal that they'll sell to customers. This is, of course, it's not just sulfur and mercury. There are often other things that are measured in the coal, but sulfur and mercury are two important ones. Sulfur, of course, because of atmospheric pollution. Mercury, also for atmospheric pollution from burning coal, of course, is very toxic to humans. I will not show real data, though, throughout this presentation. I'll use simulated data to make the points that I want to make as we go through. So this is not real data that I'm going to show from the SRM today, but it's plausible. It's plausible data. So here's the data set I'm going to use throughout the presentation. Well, actually, a picture of it. This is a little larger data set maybe than I would typically see, but it's not completely out of the realm of possibility. So on the x-axis, the horizontal axis here, we've taken measurements, and again, this is why I wanted to introduce the example scenario, is because I could call the factors bottle and day. So across the x-axis shows 6 distinct bottles, meaning I'm thinking of measurements taken on 6 distinctive bottles. The vertical axis, called it just Y here. I've omitted units, but for coal SRMs, that would typically be the SI unit for mass fraction, which is milligrams per kilogram. I've omitted the units here again because it's simulated data. The points in this graph represent individual measurements, and I've colored them according to 5 different days. So imagine that on day number 1, we take 2 measurements from bottle 1, 2 measurements from bottle 2, 2 measurements from bottle 3, so on and so forth. We repeat this for day 2, repeat it again for day 3, so on and so forth. And this is done for 5 days. So we have 60 total measurements, or 6 bottles times 5 days times 2 measurements per day. Now, as I said, I'm going to attack this problem from a predictive model sort of point of view. Well, what's the simplest possible model that we can fit to this data and use as a predictive model? So supposing that we want to predict a new hypothetical value from one of these 6 bottles. The simplest thing we could do is call the predicted value the mean of all 60 observations. And I've imposed the mean of all 60 of those measurements on this graph using with it's the red big horizontal line there. Well, you may be sitting there saying to yourself, well, you know, pretty obviously that is not the best we can do just simply looking at this plot of data. Another natural thing to do is make the predicted value, so prediction for a new hypothetical observation from one of those bottles, as the mean of the bottle. And in this graph, the bottle means are indicated with the red dot. I'm going to call this second, more complicated model the one-factor model. Of course, the one factor is the bottle. Well, again, attacking this problem from a predictive model way, we can compare the predictive abilities of those 2 models, the simple model and the one-factor model. So again, 2 graphics on this slide. The right graphic is associated with the simple model, so just the mean of all the observations. The left graphic, is associated with the simple model, and the right graphic is associated with the one-factor model. Oh, hold on, I have a couple of questions here. Okay, I'll get back to those in just one moment. Let me finish this slide, and then I'll stop and get back to those questions. Okay, so the left graphic is associated with the simple model, and the right graphic is the one-factor model. The horizontal axis on these graphs is the predicted value of the model, and the vertical axis is the actual measurement. As you would expect, all the points fall in a vertical line for the simple model because there's just one predicted value, the mean of all the observations. For the one-factor model, there are 6 vertical lines of points corresponding one to each of the one for each of the bottle means. And I would say very clearly that the one-factor model has more predictive ability, better ability to predict the values than the simple model, because the diagonal line, the straight black line on this graph, is the 45-degree line, or the 1-to-1 line. And a model with perfect predictive ability, the points would follow exactly that line. Neither one of these models have perfect predictive ability, but you can see that the one-factor model, there is a slope to the points, and that slope corresponds very closely to the 1-to-1 line. Okay, this is actually just a qualitative comparison. And the one-way analysis of variance table that I'll look at, I'll show on the next slide, is a way to change that qualitative comparison into a quantitative comparison. All right, so a couple of questions. I'm going to pause for a moment and answer questions. The first one, I'm aware of simple and 1- and 2-way ANOVA in Excel, but are there inexpensive software apps for doing ANOVA? The answer to that question is yes, there are inexpensive apps for doing ANOVA, or there is inexpensive software. I use R I use R to create the ANOVA tables that I'll show throughout this presentation. but I won't focus on software in this presentation, or at least I won't focus on showing how to use one software package, because there are actually many software packages that are available for doing ANOVA. The software used to create the graphics shown, so again, this is, I used R and the ggplot package for R to make these graphics. Okay, so I've answered what software I typically use for my work, which is R. The third question is, where does the bottle variation come from? Okay, I'm going to answer this question, where does the bottle variation come from, in two different ways. So the first way, imagine the process of grinding a batch of coal, mixing that coal up, that ground coal up, and then bottling it. You can imagine that not every bottle will have exactly the same amount of material in it. That's the target, is to have exactly the same composition of the material in each bottle, but it's very difficult to make a process so that each bottle has exactly the same composition of coal. I'm going to answer this question one more way about where the bottle variation comes from, and that is, since I simulated this data, I did artificially introduce differences between the bottles, and I embellished it a little bit to make that point. The standard reference materials, while some of them do have some bottle-to-bottle variability because constituents are difficult to homogenize between bottles, it's often not as pronounced as what I'm showing in this data set. Okay, so here is a generic one-factor ANOVA table. I've shown it here with 4 columns. When I show the output from the results of actually doing this, I'll add 2 more columns, but those will be natural by the time we get there. There are 3 rows to the ANOVA table. So the first one is associated with the factor. So in this case, the factor name would be bottle. That factor has a degrees of freedom associated with it. It's the number of factor levels. So recall there were 6 bottles, so 6 levels of the bottle factor minus 1. So the degrees of freedom associated with bottle here would be 5. There is a column for something called sums of squares, and I'm going to pause and come back to that column in a moment when I talk about the sums of squared error. And then there's a column for mean squares, which is just the sums of squares divided by the degrees of freedom. That's the first line in the one-way ANOVA table. The second line is the error line. The error line also has a degrees of freedom, which is the total number of measurements. In this case, it was 60. In our SRM example, it was 60. The number of levels of minus the number of levels of the factor. So in this case, there were 6 bottles, so 6 levels of the bottle factor. 60 minus 6 is 54 error degrees of freedom. There's a sums of squares error line, and that's where I'm going to tell you exactly what this one is. So if you take measurement minus predicted value, that gives you the residual, and the sums of squares error is squaring each of those residuals and adding them together. The third line in the one-way ANOVA table corresponds to the total, and this is where we're going to come back to this idea of partitioning variability. The total line has the number of measurements minus 1 degrees of freedom, so 59. And then the sums of squares associated with the total line is, remember, the simple model. So if you use the average of all the measurements as your predicted value, and you calculate your residual relative to that, so measurement minus the mean of all the measurements, you square those and add them together, and you get your sums of squares total. Now, the sums of squares total we can think of as a predictive ability of the simple model, the error associated with the simple model, prediction error associated with the simple model. The sums of squares error line we can interpret as the predictive ability of the one-factor model. So it's the error, predictive error associated with the one-factor model. And here's where the partitioning part comes into play. The sums of squares associated with the model plus the sums of squared error equals the sums of square total. So you're partitioning the total sums of squares into variability associated with the bottles, variability associated with the error, so what's left over from the bottles relative to the total. Small values of the sums of squares error would favor the one-factor model, the predictive ability of the one-factor model, over the predictive ability of the simple model. I'm going to pause before going on to the next slide and answer another question. I think there was another question. Actually, there wasn't. Sorry, I missed that. I thought there was another question, but it doesn't look like there's another question now. So, oops. Went too far. All right. Small values of the sums of squared error favor the one-factor model over the simple model. But how small is small? How small must it be before we favor the one-factor model over the simple model? And the answer is you can't define it in an absolute global sense. You can only define it in a relative sense, relative to the total sums of squares. And so we need another quantity, which I'm going to call F, and it's going to be obvious in just a moment why I call it F, but I'll call it F, the F test statistic, which is the difference between the total sums of squares and the error sums of squares, normalized, divided by the difference in the degrees of freedom associated with each one of those. And then that quantity ratioed with the mean square error. So it's the mean square treatment. You simplify that, it's the mean square treatment divided by the mean square error. And if you stare at this long enough, you stare at this formula long enough, you will come to the conclusion that small values of error sums of squares correspond to big values in a global sense now, because we've already done the normalization, getting the putting things on a relative scale. So now we can talk about big values of the F test statistic. And how we decide on whether the F test statistic is large or small is relative to the F probability distribution. Okay? And usually there's not a, we don't do a direct comparison of the F probability distribution with this F test statistic. We calculate a p-value, which is the probability of exceeding our F test statistic based on the F probability distribution. Okay? And usually require small values, small p-values, so less than 0.1 or less than 0.05 or less than 0.01 to support the one-factor model as opposed to the simple model. And this is a lot like Occam's razor. Unless we have strong evidence in favor of the more complicated one-factor model, we're going to prefer the simple model, just a global mean. Now, this is most usually done, so there have been a couple questions about software already. This is most usually done in software. I'm sure that I've calculated F statistics by hand before, but I don't do that anymore. Again, I mostly use the R language to do this. All right, so I'm going to switch slides, but I know there's another question that came up, so I'm going to answer that before getting to the results of the analysis variance for our simulated data set. Would you explain the sums of squares total one more time? Yes, I will. Let me go back to a previous slide to explain the SST, or sums of squares total, again. Let me go back to my graphic. So let's go to the simple model graphic. So the sums of squares total, if you take each of those points on this graph and you take its distance to the red line and you square that distance, and then you add them all together, that's the sums of squares total. Okay? The sums of squares error for the one factor model, I'll touch on that again. You need to consider this graphic, and you take the distance between each of the colored points on this graphic, not the big bright red ones, but the pastel colored points. You measure the distance from the pastel colored points to the red, their corresponding red dot or bottle mean. You square that distance, add them all together, and that's the sums of squared error. Okay. So here's the results for the one factor model. You'll notice that in comparison to the previous general ANOVA table, one-way ANOVA table that I wrote down, there are seven columns, 6 columns instead of 4 columns, and it's missing the third row, the total row. So the 2 extra columns correspond to the F statistic and the p-value. So that's why I said they would be natural after we got to these results. And we can recreate the total line just by adding the degrees of freedom together. So 59 total degrees of freedom, and adding the sums of squares row together would give us the total sums of squares. So this p-value is 0.0043, so much less than, for example, 0.01. So we would say that the one factor model adds a statistically significant improvement in predictive ability above the simple model, the simplest model. Moving on, we had one factor. We can also have 2 factors. And of course, there's a natural second factor here, day, because not only did we have 6 different bottles, we measured the bottles on 5 different days. So in this graphic shows the same data set I've been working with. We've been working with the round pastel colored points. The triangles, the big triangles, now show predicted values from a 2-factor model, adding in day as a factor. Okay, so to try to improve the predictive ability of our model. A couple more things to point out. The first thing is you'll notice that the triangles are not the mean value of the 2 points associated with a combination of bottle and day. So take, for instance, bottle 1, day 2. So the gold points in the upper left-hand corner of the graphic. The triangle is below the 2 values. So you can clearly see it's not the mean of those 2 values. That's not the predicted value for this 2-factor model that includes a bottle, and I'm going to use the term main effect, a bottle main effect, and a day main effect to introduce a little more terminology. The other thing that I want to point out about the predictions from this model is that if you look at the predictions across bottle, you'll see that for each day, the predictions run in parallel. What do I mean? Well, on bottle 1, the difference between the prediction from day 1 and day 2 is exactly the same as the difference between day 1 and day 2 for bottle 2. And exactly the same as the difference between day 1 and day 2 for bottle 3. You can see those triangles, they move together across bottle in a parallel way. I'm going to revisit that shortly when I talk about interaction terms. Okay, so this model, this two-factor model that has a bottle main effect and a day main effect, does not yet have an interaction term added to it, which forces the predictions to move in parallel across bottle. So again, we can qualitatively compare the predictive abilities of the model of the two models by plotting the predicted values on the horizontal axis and the actual measurements on the vertical axis, and seeing how well those plots, the points on the plot, line up with the 1-to-1 line or the 45-degree line. And I would say very clearly that for the two-factor model, they fall closer together. They bunch up nearer to the 45-degree line than for the one-factor model. But also, again, a two-way ANOVA table gives us a way to express that quantitatively. So you'll see a similar format for the two-way ANOVA table as the one-way ANOVA table. 4 columns, a source column, which now has two factors, a factor A and a factor B. So in our scenario, it's bottle and day. Bottle and day each have degrees of freedom associated with them, which is the number of levels of the factor -1. So for the bottle factor, 6 minus 1 is 5. For the day factor, 5 minus 1 is 4. There's an error, there's a line for the error again. So what's left over after accounting for factor A and factor B? It's the partitioning part again. The degrees of freedom associated with that is the number of measurements minus the number of levels of factor A minus the number of levels of factor B, and then we have to add one in because those 3 degrees of freedom have to sum to the total degrees of freedom, which once again is the number of measurements -1. 60 minus 1 is 59. That total line, that bottom line, will always be the same. It will not change. It will not change depending on how many factors you put into the model. Okay, the total it will always be n-1 total degrees of freedom, and the sums of squares total will always be as I described it before. The sum of the square difference from each measurement to the overall average of the measurement. That line doesn't change, but all of the other lines will change, and you'll see that as we move, as I show the numerical values for our simulated example. Now we interpret for the two-way ANOVA table, we interpret the sums of squared error as the predictive ability of the two-factor model, since we have two factors in our model. Lower sums of squared error means better predictive ability again. And we also see this partitioning effect. So the sums of squares associated with factor A, or the bottle, plus the sums of squares associated with factor B, or the day in this case, plus the error sums of squares is going to equal the total sums of squares. Now you might be thinking to yourself that the sums of squares associated with factor A wouldn't change when we add in factor B. So we'll add in another line for sums of squares. That'll change the sums of squares error, but it also changes the sums of squares associated with factor A. I want to point that out. In the two-way ANOVA table, again, we have our third column, which is the mean squares, or the sums of squares divided by the degrees of freedom. All right, so once again, smaller sums of squared error would support the two-factor model over the one-factor model. But how small must the sums of squared error for the two-factor ANOVA be before we would choose the two-factor model over the one-factor model? And again, you have to talk about large or small in relative terms. And the relative terms is relative to the sums of squared error for the one-factor model. So we define another F statistic, or it looks different, but it's really not different. I've just used a little bit of different notation to describe it, different terms to describe it. But we look at the difference in the sums of squared error from the one-factor model and the two-factor model. We ratio that with the difference in the degrees of freedom, or normalize it to the number of degrees of freedom associated with that difference. And then we take that ratio and we normalize it to the mean square error for the two-factor model. And again, we can talk about the F statistic being large or small in global terms and absolute terms, and we do that according to the F probability distribution. Large values of the F test statistic here, again, if you look at this long enough, would correspond to small values of the sums of squared error for the two-factor model. All right. So here's the results of the two-factor model, and you'll look at this slide and you'll say, hey, wait a second. This is nothing like the two-factor ANOVA table, the general one you showed just a couple of slides ago. What's going on? Why present the different results? Well, I'm going to show these results first, and then I'm going to come back to the two-factor ANOVA table and show the differences. So what's on this table? On the first row of this table, you see the error degrees of freedom associated with the one-factor model, so 54, and the error sums of squares, so the SSE, which is denoted on this slide RSS, residual sums of squares, instead of SSE, sums of squared error. And then the second row on this one is you see the degrees of freedom associated with the two-factor model, so 50, and the error sums of squares associated with the two-factor model, 41.08. You take those are the components you need, those degrees of freedom, residual degrees of freedom, and residual sums of squares. Those are the four components you need to calculate the F statistic from the previous page, which is 35.46 with a p-value of essentially 0. And then the conclusion you would draw is that adding day as a factor, as a second factor to your model, statistically significantly increases the predictive ability of your model. So why in the world did I bother writing down the general two-way ANOVA table? Well, in balanced cases, and that word is important, and as soon as I draw talk about the two different tables, I'll come back to what balanced mean. In balanced cases, the two-way ANOVA table gives you everything. It gives you the F statistic. You can calculate the F statistic right off of the two-factor ANOVA table. So I showed two tables on this slide. The top table is the one from the previous slide, just directly, you'll recognize it. And the second one is the two-way ANOVA table for the simulated data set. And what you'll notice is that the F value associated with the row in the two-way ANOVA table is exactly the same as the F value on the table from the previous slide. And the F value in the two-way ANOVA table is just the mean squares associated with the day factor divided by the mean squares associated, the mean square error, the mean squares associated with the residuals. Okay? Another thing that the two-way ANOVA table gives you is you'll see there's also an F value associated with the bottle row. You might be saying to yourself, or I don't know if you remember, but 13.88 is the F value associated with the bottle row. That's actually different than the original F value that we calculated from the one-way ANOVA table. And the reason is it has a different interpretation. So the F value associated with the bottle row in the two-way ANOVA table is now the one factor model is including day, and then we're adding bottle to get to the two factor ANOVA table. And so that's why the F value in the two-way ANOVA table associated with bottle changes from what it was in the one-way ANOVA table. Regardless, we see that day and bottle are still, no matter which order you add them in, they add a statistically significant amount of predictive ability. Back to what I mean by balanced. Recall, in this case, for each bottle on each day, we make two measurements. We always make two measurements for each combination of the factors. That's what I mean by balanced. If on one day we were to make three measurements for a specific bottle, or we couldn't make two measurements, we only made one measurement on one of the bottles for one of the days, we would no longer be in the balanced case, and we wouldn't want to use the mean squares and the F statistics directly from the two-way ANOVA table. We would want to calculate the the sums of square error associated with the one-way ANOVA table, the sums of square error associated with the two-way ANOVA table, and calculate the F statistic as I showed back on this slide, in the middle of this slide, as opposed to ratioing the mean square associated with the factors to the mean square error from the two-way ANOVA table, because in unbalanced cases, the F statistic on this slide is not the same as the ratio in the mean squares. And the one you want to use is the F statistic that only incorporates the sums of squares of error from the two models, because that is how you that's how you make the change in predictive ability. You can judge the how much change in predictive ability you've gained by adding a factor. Check for questions. All right, moving on. Interaction. So now that we have two factors instead of just one factor, I introduced the term main effect already, but now I can also talk about interactions. Two plots here. The plot on the left shows an interaction. The plot on the left shows no interaction. The plot on the right shows an interaction. So what that means, you can imagine I haven't imposed a scale here. I've just left the vertical scale and the horizontal scales blank. But the vertical scale represents the mean level of the response. So in this case, the mean measurement of the amount of substance in one of the bottles of coal. On the horizontal axis, I'm imagining a factor A with only two levels, a 0 factor and a 1 factor, and a second factor which I've called B, also with two levels, 0 and 1. So if there is no interaction, if you look across the levels of factor A for level 0 of factor B, you'll see a decrease in the mean response if I'm looking at the left side, so the no interaction plot. Now when we go to level 1 of factor B and look across the two levels of factor A, we'll see the same decrease in the mean response as we did at the 0 level. So the change, no matter what level of B you're looking at, the change across the levels of factor A is always the same, leading to the parallel lines. In the interaction case, that's not so. For level 0 of the B factor, looking across the levels of A, the mean response decreases across the levels of factor A when B is 0. But for the level 1 of B, as you look across the levels of factor A, the mean response increases. The lines are not parallel anymore, and that's what I mean by an interaction. I'm going to call, when I add the interaction term to the two-factor model, that's what I'll call the full model. And I have showed here the same data set I've been displaying as the circles. And now predictions from this full model are depicted by the triangles. And now you'll notice that the triangles are actually the means of the two measurements made on a particular combination of bottle and day. And further, no longer do you see, as you look across bottle, the gold triangles no longer move parallel to, for instance, the pink triangles. Okay? And that's what you get with the inclusion of an interaction. We can make our same predictive look at the predictive ability of the two-factor model versus the full model. I would say here the full model appears to give better predictive ability, but it's not perfectly clear from this comparison, to me at least. It looks better, but it's not obviously so. The full two-way ANOVA table, again, gives us a way to quantify that increase in predictive ability. And all we've done for the full two-way ANOVA table is add another row associated with the interaction term. It also has the degrees of freedom, which is the product of the degrees of freedom for A and the degrees of freedom for B, which since all the degrees of freedom for each row have to add up to the total degrees of freedom, that modifies the error degrees of freedom, you'll notice. Again, the sums of squared error quantifies the predictive ability of the full model. Small values of the sum of square error would prefer this full model over the original two-factor no interaction model. And you see the same partitioning of the total sums of squares into that associated with factor A, factor B, the interaction, and what's left over in the error. We can again ask the question, well, how small must the sum of squared error be before we would actually prefer the full model over the two-factor model without an interaction? Define exactly the same F statistic as I defined before, but this time the SSE2 is the sums of squared error from the full model, and the SSE1 is the sums of squared error from the two-factor model but without an interaction. And here are the results of that. The F value associated with the interaction is 2.76, which corresponds to a p-value, pretty small p-value, 0.0058. I would call that a statistically significant result, meaning that adding the interaction to the two-factor model without interaction statistically significantly increases the predictive ability, our predictive ability. But this is curious. This is actually a false positive. Remember that I simulated these data, and actually when I simulated them, I did not include a interaction term. So that's a false positive result. That of course happens. Another interesting thing about the two-way, this full two-way analysis of variance table is I want to interpret for you the F value associated with bottle and the F value associated with day. So the F value associated with bottle is a comparison again of models. It's a comparison of the full two-factor model with the interaction term relative to the model that just includes the day main effect and the bottle day interaction. The F value associated with day is the synonymous comparison. So you compare the full two-factor model with the interaction term to the model that just has a bottle main effect and a bottle day interaction. We can always interpret these F values as a comparison of a larger model, a more complicated model, and a simpler model. But the F values that come from directly from the ANOVA tables, you'll only want to use those F values or the ratios of mean squares when you're in a balanced case. Otherwise, you need to actually calculate the sums of squares error associated with the less complex model, the sums of squares associated with a more complex model, and calculate the F statistic as I've shown it on previous slides. And again, most softwares give you the ability, are included, to do that comparison without actually having to do them by hands. You just have to learn how to do it for the software that you're using. Now that basically finishes what I had to say about analysis of variance, but no discussion on analysis of variance would be complete without talking about residual diagnostics. Residuals, as I've mentioned already, are the differences between the measurements and the predicted value from the model you're fitting. Your residuals should be centered at 0. They should have constant spread and follow the normal probability distribution. You can assess the residual, you can assess centered at 0 and constant spread using residual versus predicted plots. You can assess the normal probability, whether or not they follow a normal probability distribution using a quantile plot. But things are not perfectly that simple, because there are actually two different kinds of residuals that you can think about. The raw residuals, which are just the differences between the measurement and the prediction, or the studentized residuals, because it turns out theoretically the raw residuals do not have a constant spread, but we can correct for that. And those corrected residuals are called studentized residuals. Those should always be the preferred residuals to use for residual diagnostics, but you can use raw residuals if the studentized are not available. You just need to keep in mind that the diagnostics may look slightly different, may look not as good as if you were to use studentized residuals. Okay, so here are 4 example residual versus predicted plots. The one in the upper left-hand corner is a good one. The other 3 are not so good. The first one, the upper right-hand corner, shows residuals with an increasing spread. The horizontal line in these cases marks 0 in each of the cases. The bottom left-hand plot, they're not centered around 0. You can see a clear linear trend. Again, the lower right-hand side, the residuals are not centered around 0. There's a clear quadratic trend to those residuals. Those are some common patterns you might see in residual versus predicted plots. There are others, but those are some common ones. Here is the residual versus predicted plot for the full model in the example in the simulated data set we've been looking at. It looks really quite good to me. Perhaps the variability at the lower, on the right side, so lower predicted values, and the left side lower predicted values and the right side higher predicted values, you see kind of a smaller spread there. That could be due to the inclusion of the interaction term, which was not actually used to generate the data, or it could be an optical illusion. You don't want to over-interpret these plots. They're again, qualitative diagnostics, not quantitative diagnostics. Here are 2 different example quantile plots. You are looking for the points to line up in a straight line. The one on the left is a good one. I really did generate those from a normal distribution, even though you do see a little bit of waviness. Those are pretty good. Again, you don't want to over-interpret these plots. The one on the right is clearly bad. It does not follow a straight line. It's kind of curved upwards, not quite like a bowl, but there's some definite curvature to the one on the right. Here's the quantile plot for the residuals from the full model. It looks really quite good, and of course that's because I simulated these data from a Gaussian distribution. So not surprising, it looks good here, and I added the 1-to-1 line, the 45-degree line for comparison. That ends my presentation. I'm happy to take any more questions that you might have. And this reference on this slide, I'll leave it up here for a bit while I take questions, is a very comprehensive reference for ANOVA and more generally linear models. So I don't actually, oh, here's another question. Okay. Can you talk about how to interpret main effects when there is a significant interaction? Yes, that's a good question. I can talk about how to interpret main effects when there's an interaction. So you can think of it, as long as everything is balanced, you can interpret the main effects as the average change across all the levels of the other factor that you expect. So if I go back to, let me see, I go back to this plot, the interaction plot. So if you look at the plot on the right, you have, you see that the lines aren't parallel. There's an interaction. So for one level of factor B, you actually see a negative main effect of factor A. And for the other level of factor B, you would see a positive effect. So essentially what you would see is the main effect for factor A would be 0. It doesn't always work out that way. That's just how I made the graphic. But you would interpret that main effect of A as the average main effect across all the levels of factor B. In non-balanced situations, that interpretation doesn't hold perfectly, and it becomes more difficult to interpret main effects in the presence of interactions. And I would, in that case, again, I would fall back. I would try to give them predictive interpretations. I would look at predictions from my model and interpret them in terms of those predictions. It's difficult to give a general answer in the non-balanced case. Very good question.
So Adams, this is
Yes.
Steve again.
Yep.
I don't see any other questions. I just wanted to remind folks that the Statistics Division has a YouTube channel. So if you go to youtube.com/ASQ Stats Division, you will find eventually this presentation, but other recorded webinars on introductory topics. We did one about 6 months ago on regression. We've done one on acceptance sampling, so those are good to view. Next month, we will return back to our more normal daytime presentations. And the topic next month will be not statistical. It'll be on benchmarking, presented by Grace Duffy, who is an international expert on that topic. In closing, anything else you want to add, Adam?
I think that's it. I actually talked a little longer than I had intended to. When I looked up, it was 8:45. So I think I've said all that I had intended to say and more, unless there are other questions. I see one more question that just popped up, Steve, so give me a second. Oh, just an FYI, the YouTube link didn't work as included here. Okay. Where is here, if I might ask the question asker?
in the chat box, there is one message that says, "Welcome to our webinar. We will begin shortly."
Oh, okay, okay, yes. The peer. I see what you mean. The punctuation there messes that up. Okay, all right. Thank you very much. We'll I'll see if I can change that actually before the next webinar. Thank you. All right. So thank you everyone for attending the webinar, and I hope that it was helpful. Steve?
Thank you very much, Adam. And to the rest of you, go to the ASQ.org Statistics Division website for this and other information about our division and other offerings we have planned for 2018. Thank you, and have a good night.